Hi, this is the video for section 4.4 of a student's guide to the Schrödinger equation. This one's all about Fourier theory and the formation of quantum wave packets. It starts out with a paragraph that mentions that there are really two major aspects of Fourier theory. Those are analysis and synthesis, and if you work through the earlier chapters, you've seen both of these at least briefly. In section 1.6, we talked about how you can use the inner product to find the components of a wave function, and that's essentially what Fourier analysis is, trying to figure out what are the components of a given function. That's also called spectral decomposition. Then, in section 3.1, we talked about producing a composite waveform by weighting and adding several different plane wave functions in order to achieve some desired effect, like spatially limiting the resulting function. That's the essence of Fourier synthesis. So in this section, there's going to be more detail about Fourier theory, specifically why the Fourier transform is so key to both analysis and synthesis. And the last half of this section is all about forming wave packets and what that has to do with the uncertainty principle. First equation in this section is the Fourier transform. It says that phi of k, some function of wave number k, is equal to some constants, we'll talk about those in a minute, times this integral of a position wave function, psi of x, multiplied by this factor, e to the minus ikx, and that whole thing integrated over x. So what is it really telling you? It's telling you if you know your position function, psi of x, and you want to know what's the function in wave number space corresponding to that position space wave function, psi of x, this is how you get it. Let's clean that up a little bit. So given a psi of x, you plug it in here, do this multiply, do this integral, multiply by this factor, and that's your wave number function phi of k. We'll say more about this in a minute, but first, have a look at the inverse Fourier transform. In this case, you're given the wave number function phi of k, and you want to know what is the position function corresponding to that. Well, it's a very similar but not identical process. In this case, you multiply by e to the positive ikx, and you integrate over all wave numbers. You have the same factor in front here, and that's one reason that factor is there. It just makes what some people call the forward Fourier transform symmetric with the inverse transform. So what's really behind these equations? Well, there's a little summary here, which says any well-behaved function, we'll say what well-behaved means in a minute, can be expressed as a weighted combination of sinusoids, that is, sines and cosines. So in the case of a position function, such as psi of x, those sinusoidal functions are cosine kx and sine kx, where k is the wave number of each component that's going to go into making up psi of x. As I mentioned in the previous section, k is sometimes called a spatial frequency because it has dimensions of angle per unit length, that is, radians per meter in the SI system. So to understand what the Fourier transform is telling you to do, think of it this way. You've got a position function psi of x, and you want to know how much of each sine or cosine function, sine or cosine of kx, is present in psi of x for each wave number k. What the Fourier transforms tells you to do is to multiply psi of x by this e to the minus ikx factor, and I think it's helpful to think of that as cosine kx minus I sine kx by Euler's relation. Once you've done that, multiply, then integrate over all space, that is x equals minus infinity to infinity, and the result of that process, once you throw in the 1 over the square root of 2 pi factor, is phi of k. Now understand, since we're multiplying by cosine kx minus I sine kx, the results of this process could well be complex. But here's the way I think of it. If psi of x is real, then the real part of the wave number spectrum, phi of k, tells you the amount of cosine kx for each k that is present in psi of x, and the imaginary part of phi of k tells you the amount of sine kx for each k that is present. Before I get into the details, I should point out that in this footnote, well-behaved is defined. It says any function that satisfies the Dirichlet conditions. That means that there are no more than a finite number of extrema and a finite number of infinite discontinuities in the function. You can read more about that in the glossary on the app, where there will be some links to other sources about what exactly the Dirichlet conditions mean. If you want to understand why this process of multiplying and integrating tells you how much of each sinusoid is present, I think it helps to start out by writing the Fourier transform like this, and then using the Euler relation to turn this e to the minus I kx into cosine kx minus I sine kx. I find it helpful to think about this for a function psi of x that's a simple sinusoid itself. Say it's a cosine function. Maybe it's got a single wave number, which I've called k1. So if psi of x is cosine k1 of x, what does the Fourier transform tell you to do to figure out how much of each k there should be? Now you know the answer already. The only cosine present should be cosine of k1x, because that's what our psi of x function is defined as, and there should be no sine kx present at all, because we're trying to make up a cosine. So let's see what the math tells us. Here it is, written out with cosine k1x plugged in as psi of x. And at this point, most authors introduce the orthogonality relations. You may remember what those say. Clean this up a bit. They say when you have an integral over all x of a cosine times a cosine, that's going to yield 0 unless the argument of this cosine exactly equals the argument of that cosine. In other words, only when k equals k1 will this integral yield a non-zero value. The orthogonality relations also say when you have a cosine times a sine that is integrated over all space, that's going to yield 0 in every case, because those two functions are orthogonal. So the orthogonality relations tell us exactly what we expected to get. Only when k equals k1 will that cosine times cosine integral yield anything, and the sine integral will always yield 0. So what we'll get for phi of k is just cosine of k1x. But if you want to understand why that's true, I think a figure like this is helpful. Here's our psi of x, the original cosine of k1x. Cosine function, and over this range of x, I've drawn a couple cycles, but remember, it's a cosine. It goes all the way to negative infinity in negative x and all the way to positive infinity in positive x. Now we're going to multiply that by the real part of e to the minus I kx. That is, cosine kx. Remember, we're going to multiply it by cosine kx for all these different k's, but in this case, I've just shown the cosine for k equals k1. And what happens when you multiply these two functions? Clean this up. Here's our function psi of x. Here's cosine of kx for k equals k1. They're both positive. They yield positive. At this point, they're both negative. Multiply those together, you get a positive. Positive times positive, you get another positive. Negative times, they're always the exact same sign, and therefore when you multiply them together, you always get a positive value. Sometimes it's very small when they're both small, but it's always positive, never goes below 0. So when you integrate this, you're essentially finding the area under this curve, and it's going to be a big number. It's actually going to be infinity if you integrate all the way out to positive infinity and negative infinity. So multiplying psi of x, when it's cosine k1x, by the real part of e to the minus I kx, gives a very big number because the positive and negative values match up perfectly, and the result of the multiplication is always positive. Now let's see what happens when we multiply psi of x, which is still cosine k1x, by the imaginary part of e to the minus I kx, but we are, again, going to only take the one where k equals k1. So the wave numbers match perfectly, but this one is a minus sign, because we're doing e to the minus I kx. So here's a minus sine wave, and look at what happens when you multiply our cosine k1x times this minus sine of k1x. Plus times minus is minus, minus times minus is plus, minus times plus is minus, plus, minus, plus, minus. I think you see where this is going. When you run this out all the way to infinity and minus infinity, you have exactly as much area above as below, and you get 0. Just as the orthogonality relation said, the sine integral when psi of x equals cosine of k1x is 0. Now, before we see what happens when you multiply by e to the minus I kx with different values of k, there's a paragraph here that points out that the Fourier transform produces precisely 0 for the imaginary portion, that is, the sine portion, if you integrate all the way out to infinity. But it also produces 0 if you integrate over an integer number of cycles. Because if you do an integer number of cycles, then there's exactly as much plus as minus resulting from those products. But if you don't integrate over an integer number of cycles or all the way to infinity, say you do 1.5 cycles, then there might be some residual positive or negative. So you'll get exactly 0 when you integrate from minus infinity to infinity, or from minus t over 2 to t over 2, where t is the period of the periodic function that you're analyzing. But if you integrate over another interval, you may not get exactly 0. As it explains here, the more of the x-axis over which you integrate, the smaller the effect of that residual is going to be. That is, the ratio of the imaginary part to the real part, in this case of psi of x being cosine of k1x, can be made arbitrarily small in comparison to the real part by integrating over a large range of x. So now the question is, what happens when we multiply by e to the minus ikx for other wave numbers k? You can see one example of that here in figure 4.7. This is still our psi of x, cosine k1x. Now I've let k, that is, the wave number in the e to the minus ikx function, equal half of k1. That means, since the wave number is inversely proportional to the wavelength of this function, if you will, the testing function, is going to be twice as big as the wavelength of psi of x. I call it a testing function because it tests whether that k is present in psi of x. Now what happens when you multiply these two functions? Here's plus plus, here's minus plus, here's minus minus, that gives plus, here's a plus minus, that gives minus, and do each of these multiplies. It's really a continuous process. I'm just showing a few examples here, and look at what you get. You get as much area below the axis as above the axis. So once again, if you integrate all the way out to positive and negative infinity, or over any integer number of cycles, this will yield 0. So even though we're multiplying a cosine by a cosine, if those spatial frequencies, that is, those wave numbers, don't match, the result of the Fourier transform is 0. We can also go the other way. Here we've taken the real part of e to the minus ikx, but we've let k be twice as big as k1. That means the wavelength is half as big. So now this function has a much shorter wavelength, and look at what happens with these multiplies. Plus minus, minus plus. Once again, there is as much area above the x-axis as below. And that means that this will also yield 0. So as it explains here, anytime k does not match k1, the orthogonality relation tells you that the Fourier transform process will give 0 if you integrate to infinity or an integer number of cycles. There's a little note here that says, in this case, the imaginary portion of phi of k, the wave number spectrum, turned out to be 0, because after all, we put in a cosine wave for psi of x, so you would expect the wave number spectrum to be real, and that's what we found. But it's real because our position function was a cosine wave, not because psi of x was real. If we had selected a sine of k1x as our psi of x, then the result of the Fourier transform would have been purely imaginary, because in that case, only the sine component would have turned out to be non-zero, and the cosine component would have been 0. So always remember, the result of the Fourier transform is in general complex, and how large the real or imaginary parts of phi of k are depends entirely on the function you're transforming. If psi of x has a lot of cosine in it, the real part of phi of k will be big. If it's got a lot of sine in it, the imaginary part of phi of k will be big. So multiplying sinusoids is one way to understand the Fourier transform process. Another way is to write psi of x and e to the minus ikx as phasors. If you need a little review on what a phasor is, there's a description up here that explains that phasors live in the complex plane. Remember, that was described back in chapter 1 as being an imaginary axis, usually vertical, and a real axis, in this case horizontal. And an individual phasor is essentially an arrow that rotates around the origin, and the angle from the positive real axis measured counterclockwise is called kx. Since k is 2 pi over lambda, that way, when x equals lambda, you've gone 2 pi radians. That means you've gone all the way around. And by convention, when you have e to the positive ikx, we take that as going around counterclockwise with its tip on the unit circle. Why is that helpful for Fourier transforms? Well, look at what happens if we project this phasor onto the imaginary axis and onto the real axis. As it rotates around, here's what the projection onto the imaginary axis looks like. That's a sine wave. It's sine of kx. Starts at 0 here because the projection onto the vertical axis is 0. Goes up to 1 here because it's all along the vertical axis. Goes back to 0 when it's here. Goes to -1 when it's here. And as you see, that traces out a sine wave. Had we projected onto the real axis, we would have traced this out. You have to kind of turn your head sideways to see this is a cosine kx moving in that direction. Clean this up. So phasors are a very useful way to represent sinusoids. And if this angle in the counterclockwise direction is kx, you can probably guess what e to the minus I kx looks like. That's a phasor that rotates around this way, the opposite direction, because of this minus sign. So with that background, we're ready to talk about phasors in Fourier transforms. Well, just like we did when we were doing sines and cosines, we need to have a position function, psi of x, and we're going to let it be the complex function e to the I k1x. In other words, we're going to select a single wave number, k1, just like we did before, but now we're representing psi of x as a complex function. And we want to know, how does the Fourier transform work in that case? In this figure, you can see our e to the I k1x function. It's rotating around since we have positive exponent in the counterclockwise direction. The angle at any given value of x is given by k1x, and I've just picked 8 positions to show that phasor. It's actually continuously moving as x increases. So what does the Fourier transform tell us to do? It says if you want to know the wave number spectrum, multiply psi of x by a series of exponentials e to the minus I kx. So what does that look like? Well, I've shown it here for a specific k, and I picked k1, the same wave number as our psi of x, which is e to the I k1x. Notice we have a minus sign in the Fourier transform factor, and that means that this phasor is going to rotate around clockwise. So what happens when you multiply these two together? When you multiply phasors, you multiply their amplitudes, but you add their angles. And as this one rotates up to some position k1x, this one rotates down because it's e to the minus I k1x, so it's at angle negative k1x, and when you add those together, you get angle 0. In other words, the product of those phasors points along the real axis. And if you do that repeatedly at a bunch of different values of k1x, they all add in the same direction along the real axis. So when you look at the Fourier transform relationship, taking our psi of x, e to the I k1x, multiplying it by e to the minus I kx, you have these two counter-rotating phasors, and as long as they both have the same wave number, in this case k equals k1, when you make the product of those two functions and add them together, you get a very big positive number along the real axis. Okay, that's exactly what we hope for when k equals k1. But what about the case where the Fourier transform testing function, the one we're going to multiply psi of x by, is no longer at the same wave number? In this case, I've taken k equals 2k1. So the wave number is twice as big. That means the wavelength is half as big. But for the phasors, it means that the steps, the rate of rotation with x, if you will, is going to be bigger because k is 2k1. So the steps this phasor takes are twice as big and in the opposite direction from the steps this one takes. Well, that means that when you multiply these two together and add their angles, this one has gone more negative than this one has gone positive. Specifically, it's gone twice as far. Therefore, the resultant phasor is going to be at a negative angle. And as this one takes another step also twice as big as this step, the resultant is going to be even more negative. And as the resultant phasor keeps changing its angle, when I add all those together, you use the same rules of vector addition. You do the head to tail addition. So if this is the first one, we add the next one at a slightly negative angle, and the next one at a more negative angle, and the next one, and the next one, and the next one. We're going to come right back around at any integer number of cycles, or if we can go all the way out to infinity, the resultant phasor is going to come all the way around back to 0. So when the rate of rotation in the Fourier transform factor does not match the rate of rotation of psi of x, the phasors do not line up at the same angle, and you get a small resultant. If you want to see the numbers on that example, they're given here. And then there's another example in which we're going to take the Fourier transform factor as half of k1, where k1 is our psi of x wave number. Now, this guy takes a little step, while this one takes a bigger step in the opposite direction, and then another little step here, and another bigger step here. And that means that the resultant will move counterclockwise. It'll continuously vary the phase, and that means when you add them all together, once again, it tends to 0. So as it says here, since k does not match k1, the direction of the product phasor is not constant and it rotates. And because it rotates, when you add them all together, you get a small value. What's nice about the phasor approach is you can also use phasors for functions that aren't represented by a single rotating phasor with constant amplitude. For example, our previous case of psi of x equals cosine of k1x. You can see how to represent that in phasor world using this inverse Euler relation, where cosine of k1x is e to the I k1x plus e to the minus I k1x, all divided by 2. So that means that the cosine function, which is represented here, is actually two-phasor. This one, with length 1/2, due to the 2 in the denominator, and moving in the counterclockwise direction because it's e to the plus k1x. And this one, also of amplitude 1/2, moving in the clockwise direction because it's e to the minus I k1x. And when you add those two together, not multiplying them, adding them together, because that's what the inverse Euler tells you to do, the resultant of those two points along the real axis. When kx equals 0, they're both along the real axis, and they add up to 1. As x increases, this one rotates around this way, this one rotates around this way, and the imaginary parts always cancel, and the real parts just get smaller and smaller. I can show that here. So there's the first one, and then a little later, and a little later, and then as x continues, it's going to go this way. That's a half a cycle, and then for the next half cycle, they're going to go back. So they just oscillate back and forth along the real axis, exactly as you would expect the cosine to do. And in the Fourier transform, we're going to multiply that by e to the minus I kx for all different k's, but once again, I've chosen to show the one where k equals k1, and that means that our multiplying factor starts out here and then goes here and here and here. And when you multiply these by these, here's what you get as a result. Notice, if k equals k1, some are bigger, some are smaller, but when you add them together, all of the vertical parts, that is the imaginary parts, cancel, and you get a result along the real axis, exactly as you would expect. Had k not matched k1, had we picked a different k, then this phasor and this would not have been in the positive portion and in the negative portion at exactly the same times, and so you would have had some of these resultants over here, and once again, they would tend to add to a small value. But when k equals k1, these two are synced together so that the real part is always positive and the sum of the products points along the real axis, exactly as you'd expect for our single wave number cosine function. So when you're dealing with quantum wave functions that may be complex, you can think about phasor representations of complex psi of x, and the Fourier transform process is essentially multiplying the phasor representations of psi of x and e to the minus I kx and summing or integrating, in the continuous case, those products. Before we get to wave packet formation, I think it's helpful to look at this multiply and integrate process using Dirac notation. And to get started with that, look at this equation right here. If you worked through the earlier sections of this chapter and the previous chapters, you probably remember that this equation tells you that the wave function psi of x is given by projecting the state, represented by basis-independent ket psi, onto the position basis vectors, which are represented by x here. X is a ket, and when it appears in the inner product like this, it looks like a bra. You can use the Fourier transform to see that the wave number spectrum phi of k is the projection of the state represented by ket psi onto the wave number basis functions k. To see how to do that through the Fourier transform, remember that in the position basis, the plane wave functions 1 over the square root of 2 pi e to the I kx are the wave number eigenfunctions. And those are what you get when you project the wave number basis functions k onto the position basis functions x. The reason that's interesting is because something interesting happens when you rearrange the order of the Fourier transform expression. Bring this constant inside the integral, interchange the order of these two terms, and you get this. Now, compare this term to what we just had. It's identical, except it has a minus in front of the I in the e to the minus I kx. But of course, that's just the complex conjugate of this, right? If I take the complex conjugate, I put a minus in front of the I, and that means I must take the complex conjugate of these. But this complex conjugate is just the same inner product with the members of the inner product switched. So I'm going to plug this in for xk star, and the inner product of x and psi for psi of x, and that gives us this, which looks like this. And where did that identity operator I hat come from? That's explained right here. Remember, when you see a ket standing to the left of its corresponding bra, that's a projection operator. You can read about that in section 2.4 if you don't remember that. And in this case, since it has the position basis vectors as the projector vector, when you form the sum, or in this case the integral, over all x, that gives the identity operator. So this term, integrated over all x, becomes I hat. But I hat operating on psi just gives psi again. So here we are. Phi of k is no more than the projection of the state represented by ket psi onto the wave number basis functions k. And in the position basis, that wave number ket k corresponds to those plane wave functions. So we've looked at the Fourier transform as multiplying a function by cosine and sine functions and integrating the results, or by multiplying and adding phasors, or by projecting an abstract state vector onto sinusoidal wave number basis functions. Each of those is a perfectly valid way at looking at the Fourier analysis function provided by the Fourier transform. As it says here, Fourier synthesis is the complementary function. We're going to produce a wave function with the characteristics we want by combining sinusoidal functions in the proper proportions. What we're going to do with that is to make a wave packet which has limited spatial extent. Producing those wave packets by combining plane waves is important in quantum mechanics because, as we've said before, a monochromatic, that is, single wave number plane wave is not normalizable. Since functions like ae to the I kx minus omega t extend to infinity, both positive and negative x, the area under the square magnitude is infinite. And that means you can't normalize it, so these individual plane wave functions are disqualified because they're not physically realizable. But if we limit them to a certain region of space, they become normalizable. So that's what we want to do. We want to combine multiple plane waves in just the right proportions so they add up, that is, constructive interference in some region, and then destructive interference elsewhere. That right amount of each plane wave is given by phi of k, and the inverse Fourier transform will tell us what our psi of x looks like for a given wave number spectrum phi. A little terminology before we put some numbers into this. The Fourier transform is often referred to as mapping functions from one space or domain, such as position, to another domain, such as wave number. The functions in those two domains, if they're related by the Fourier transform, are called Fourier transform pairs, and the variables on which the functions depend are called conjugate variables. Whenever you have conjugate variables, they always obey some form of uncertainty principle, and that means you cannot know precisely both variables at the same time. And you can see that in action in the remainder of this section. I'm going to start with a pretty straightforward case where we take a bunch of plane wave functions, e to the I kx. We're going to give them each an amplitude of unity. We're going to let them exist over some range of wave numbers delta k. You can see that here. So the wave number spectrum phi of k is 0 out to some point, then it jumps up to a value of 1, stays at 1 for some range of wave numbers, and then jumps back down to 0 for all others. We're calling this non-zero portion delta k, and the middle of the non-zero portion is called k0. We're going to use the Fourier transform to determine what psi of x looks like. Here's how the math looks. This is our inverse Fourier transform relationship, and phi of k is only non-zero, that is, it has a value of 1, from k0 minus delta k over 2 to k0 plus delta k over 2. Everywhere else it's 0. Well, that's a fairly straightforward integral to evaluate. You can use this relation, and when you do the math, plug in these limits, you get this expression. A little hard to see what's going on there, but notice that this part, you can use this inverse Euler, in which sine of theta is e to the I theta minus e to the minus I theta over 2I. If we let theta equal delta kx over 2, then we can turn our terms in square brackets into this. When you plug that in, you find that this is psi of x. Still not quite clear what this looks like, but it helps if we multiply both numerator and denominator by the factor delta k over 2. You'll see why this helps in a minute. So here's a delta k over 2 in the numerator. Here's one in the denominator. These twos are going to cancel. We're going to take this and the x and move it underneath the sign. That's done here. Why did we go through that? Because now the argument of the sign is the same as the denominator of this term. So really we've got three terms here. Constant term out front. There's this sinusoidally varying term, which just looks like cosine k0x plus I sine k0x. And then this term. Before we talk about that term, there's a little paragraph here which says that the wave number k0 is just equal to 2 pi over some base wavelength lambda 0. And in the graphs, we're going to take lambda 0 as one distance unit. But what about this other part? As it says here, this is called the sinc function. I'm afraid it's misspelled in my version. I hope yours is spelled correctly. And the sinc function is simply a function of the form sine of some constant times x over that same constant times x in the denominator. And that's exactly what we've got. That sine x over x function is 1 at x equals 0, and then it oscillates down like this in both directions. These should be getting smaller as we move away from 0. This is x. That's what the sinc function looks like. By the way, if you're wondering at x equals 0 why that has a value of 1, you can use L'Hopital's rule. Take the derivative of the numerator and denominator, you'll see why it's equal to 1. But you can also figure out where this crosses 0, and as it says here, for our sinc function, that occurs at x equals 2 pi over delta k. So what does that mean about our psi of x function? Well, you can see the real part of it here. It's got a cosine k0x, which goes through one complete cycle, every lambda 0, which is 1 unit on this distance scale. And here's our sinc function, which is the envelope, if you will. The thing I drew was essentially this and this. And when you multiply that by cosine, it fills in where you see this. So when you take this range of wave numbers, delta k, and make the spectrum 0 everywhere else, this is what you get in position space. But notice that since that first 0 happens where x is 2 pi over delta k, if you want this to be narrow in position, then you've got to make delta k wide. And if you make delta k narrow, then the spread in position is going to be wide. Exactly how wide depends on exactly what spectrum you used. We used one with a flat top in wave number space, that is, k equals 1 over that range delta k. But this inverse relationship of the width in position and the width in wave number space holds for any spectrum. Here are the numbers for why the first 0 crossing appears where it does in that graph, in which we had taken delta k to be 10% of k0. But if we increase that delta k to 50% of k0, then it looks like this. Now we've got a wider range of wave numbers, still with a uniform amplitude of 1. Look at what's happened to our psi of x. Psi of x is much narrower than it was when we had a smaller range of k0. And if we want to make this narrower still, we've got to make this wider still, as you'll see in a minute. But first, let's go the other way. Let's take an even narrower range, delta k, of non-zero wave numbers. We're still keeping k0 the same. Look at what happened to our sine x over x. In the region of graph I've shown here, we barely get to that first 0 crossing. That's our sinc term now. So as it says here, even without having a precise relationship between the width of psi of x and phi of k, you could have figured that this was going to happen, because if delta k equals 0, that is, if you just take a single wave number, k0, don't let it have any width in the wave number domain at all, you know what that corresponds to? A single spatial frequency, or monochromatic plane wave. And that extends to infinity in both positive and negative directions. So when the wave number spectrum width becomes 0, the width, if you can call it that, of psi of x becomes infinite. You never have a 0 crossing. You can see something that comes close to that in this example where I've let delta k go to something like 0.5% of k0. It's extremely narrow, and look at the real part of psi of x. There's still a sinc function here, but it's barely detectable. And if I truly had let this go to 0, this would have been perfectly flat over all space. To see the mathematics of that, it helps to write the inverse Fourier transform like this. We've put a prime on the k's because we need to differentiate this integral from another. What we're going to do is take that expression and plug it in for psi of x here. So here's that expression with our primed k's. We're using the Fourier transform for phi of k and plugging in the inverse Fourier transform for psi of x. So what does that look like? Well, we can move constants inside, and since this term depends on k but not k prime, it can go inside this integral, which makes it look like this. And to see what this means, we can switch the order of these two integrations. It gives the reason we can do that here. The short answer is the functions under the integrals are continuous, and it's well behaved. We don't even have to fiddle with the limits since they're both minus infinity to infinity. And when you switch that order of integration, you get this. And why is this interesting? Look at what this is telling us. Phi of k, the spectrum at every value of k, is equal to this expression, which is the integral of phi of k prime, times this expression over all k prime. So how can the value of the function phi of k at every wave number k equal the integral of that same function multiplied by this term in square brackets and integrated over all k prime? It's as though the term in square brackets here is sifting through the entire phi of k prime function and pulling out one value, the value of phi at k. So the integral winds up not summing anything. It just takes on the value of phi of k. So how can this term in square brackets do that? Well, you know something that does work like that. It's the Dirac delta function, which, when the argument is 0, is infinitely tall, but for any non-zero argument, it's 0. Much more helpful is how it behaves when it's under an integral, like this. If you've got some function we've called f of x prime here, and you multiply it by a delta function of x minus x prime, the only place where this delta function is non-zero is when x equals x prime. And at that point, this function just walks out of the integral and becomes f of x. So the delta function does this exact sifting function that we needed up here. This guy must look like a delta function. If it does, then you can write 429 like this, where we've replaced the term in square brackets with a delta function, and there's our term in square brackets equaling a delta function. Had we gone the other way and plugged phi of k into the inverse Fourier transform, we would have come to a version in which this integral over k gives us a delta function in x. If you want to see how that works, there's a chapter in Problem, and the solution shows how that works. So now let's apply this to our single wave number wave function. Psi of x is just e to the I k0x, just a single wave number. We're going to plug that in for psi of x. So here it is. But this product looks like this, and that integral looks like 2 pi times our delta function. When you plug that in, this is what you get. So as we said, for a single wave number position function, that is, psi of x equals e to the I k0x, the spectrum is an infinitely narrow spike at k equals k0. There's a little explanation here of how the amplitudes work out in the example shown in figure 417. So that's one extreme case. We said a spike with width 0 in the wave number domain makes for a sinusoidal function in which the width approaches infinity in the position domain. What if we go the other way? You can see that down here. Now we've got an infinite width in the wave number domain, and if we combine all those wave functions together, we can get an infinitely narrow width in the position domain. Here's how that math looks. We put in, for psi of x, a delta function of x. That's shown here. And you know what this delta function under an integral does. It finds the value of the function at x equals 0. So that comes out of the integral as e to the 0, which is just 1. So phi of k is a constant. Infinitely narrow in position space, infinitely wide in wave number space. And once again, a little explanation of how the amplitudes work out here. This is summarized here. Narrow in one domain means wide in the complementary domain. That's the basis of the uncertainty principle, about which you can read a lot more in the next section. That's it for this one.